Good day everyone, thank you for coming to our presentation at GlobeCom 2021. My name is Chen and today I'll be presenting our work titled Predictable Bandwidth Slicing with Open vSwitch. So a quick overview of what I'll be covering. I will first be covering some brief background about what software-defined networking is, what bandwidth slicing is, and how bandwidth slicing is used in software-defined networks. I'll then discuss how latency can be predicted in a switching system, what prerequisite knowledge is required to do so, and demonstrate that this methodology is applicable to real-world bandwidth slicing systems. Finally, I'll discuss a couple of common approaches to bandwidth slicing and the pros and cons of each of those. First, a little bit of background about software-defined networking. Software-defined networking is a network architecture that decouples the data and control planes in a network and places the control plane in a logically centralized controller. Instead of each device making its own packet routing decisions using traditional routing protocols, such as OSPF or BGP, the routing decisions are now delegated to a logically centralized controller, which can then configure each switch according to its global view of the network. This is done by installing flow rules onto each switch. The flow rules are used to describe which routing actions should be taken for each type of packet. The use of flow rules also increases the granularity of control over each data flow, as packets can now be matched on a wide variety of potential match fields, such as port numbers, MAC addresses, or even transport layer protocols. These flow rules can then be used to direct packets into bandwidth sliced queues, thus enforcing rate guarantees and limitations for specific applications and devices. What is bandwidth slicing? Bandwidth slicing is the act of splitting up a network's bandwidth resources into discrete chunks. These discrete chunks of bandwidth can be assigned based on each user's QoS requests. For example, some users will request rate guarantees since they need the data to be sent at a specified minimum rate. Rate limitations can also be set to prevent any individual user or application from greedily consuming excess amounts of bandwidth. Rate guarantees and rate limitations are not mutually exclusive, and any data flow can be assigned both guarantees and limitations. How is bandwidth slicing implemented in software-defined networks? Bandwidth slicing is accomplished by implementing packet schedulers on network devices such as switches or routers. In this work, we analyze the bandwidth slicing performance of the Open vSwitch, or OVS. The Open vSwitch is an open-source, production-quality software switch that is compatible with various hypervisors and container systems. The Open vSwitch has two main variants. The first variant is OVS with the kernel path, that we refer to as OVS-KP. This variant implements its data path via a kernel module. As such, it can take advantage of the Linux kernel's packet scheduling mechanisms. The second is OVS with DPDK, which implements its data path through DPDK full mode drivers that operate entirely in the user space. With OVS-KP, we use the Hierarchical Token Bucket, or HTB, packet scheduler, which is widely used and available as part of the Linux traffic control module. With OVS DPDK, we use a packet scheduler based on the 2-rate 3-color marker algorithm. Since the data path is entirely in user space, DPDK is unable to utilize the Linux traffic control module's packet schedulers and must rely on its own built-in packet schedulers. It is important to understand packet latency in bandwidth slicing scenarios because now network controllers can provide not just rate guarantees for microservices, but also latency guarantees as well. In edge and fog computing scenarios, time-critical microservices can now operate with knowledge of a packet's expected arrival time. Network administrators can use this knowledge to determine whether a microservice's latency requirements are satisfiable within the current network constraints. Network administrators can also use this knowledge to design network configurations that decide between minimal latency, maximal throughput, or some balance in between. Knowledge of packet latency in software switching systems is very important, but existing literature falls short when it comes to providing a comprehensive model of software switching packet latency. First, performance evaluations of software switches are usually limited to measurements of maximum throughput through that switch. Although throughput and latency are very closely correlated, there are additional factors that have significant impact on the latency of a software switch. We explore some of these additional factors in this work. Second, existing latency measurements and analyses are usually for oversimplified use cases and do not encompass the variations in network configurations that will be encountered in bandwidth-sliced networks. These latency measurements are only applicable for their one specific situation and cannot be used in real-world networks. Accurate prediction of packet latency through a software switch is accomplished through two steps. The first step is generating a mathematical model of the switching system that can be used to then predict packet behaviors. Luckily, we can use pre-existing queuing theory frameworks as a representation of our rate-controlled queues. The second step is determining the correct values to place into the model in order to obtain accurate predictions. Although some variables, such as queue rate, might seem trivial at first, we showed that it is in fact not quite so simple, and we explained how we obtain the correct values that need to be placed into the equation. We then validate that the values we use are correct through a comparison between the observed latencies and the latencies that we predict with our applied queuing theory equations. The latency of a packet that is sent through a software switch is comprised of three components: the processing latency, the transmission latency, and the queuing latency. Processing latency is highly dependent on both hardware capabilities and software efficiency. Processing latency is difficult to predict and has a relatively small impact on the overall latency of a packet through a switch. Transmission latency is also dependent on the hardware capabilities, but it is relatively simple to predict. Transmission latency is usually not very significant when it comes to switching latency, since it is so small. Of the three, queuing latency is by far the most significant, especially in rate-limited systems. Thus, the focus of our packet latency analysis is on queuing latency caused by rate-limited queues. To model our switching system, we represent each bandwidth-sliced queue as an MM1 queue. The MM1 queue designation indicates that arrival times and service times are distributed in an exponential distribution. In an MM1 queuing system, the average wait time of a packet in the queue is represented by this equation, where mu is the queue rate and rho is the queue utilization ratio. The issue now at hand is filling in the variables of mu and rho with the correct values, which is the tricky part of latency prediction in a bandwidth-sliced system. Rho is relatively straightforward to obtain. A quick Wireshark analysis of the traffic flow through a queue will give a value for the queue utilization ratio. However, for mu, the queue rate, it is not as simple as plugging in the configured queue rate. For example, if a queue is configured for 100 megabits per second, the value of mu would actually not be the intuitive value of 100 million. This is because the queuing system does not actually dequeue the queue one bit at a time. To find the correct queue rate that can be plugged into the MM1 queue latency equation, we must first find out the granularity of our queuing system, or the effective queue rate. We determine the effective queue rate by running an experiment to observe the granularity at which packets are being dequeued from the rate-limited queues. We set up an experiment in which we set bursts of increasing numbers of packets into the queue, and then measure the latencies of the entire burst of packets. We also measure the latencies of each individual packet in the burst. In the figure on the left, the x-axis is the number of packets in the burst, and the y-axis is the total burst latency, or the time it takes for the entire burst to travel through the queue. One interesting thing to note is that a burst of 5 packets will have pretty much exactly the same latency as a burst of 16 packets. This indicates that packets 5 through 16 in a burst are all dequeued at the same time, hence the lack of difference in the overall burst latencies. In the figure on the right, the x-axis is once again the number of packets in the burst, but this time the y-axis is the latency of each individual packet in each burst. The packets near the start of the burst are closer to blue, while the packets near the end of the burst are closer to red. Once again, we can see that the packets are not dequeued one at a time, but rather in small bursts of multiple packets at once. As both figures show, packets are not dequeued individually, but rather in chunks of 16. We can now use this information to convert the known configured queue rate values to an effective queue rate values. Once we have converted the queue rates from configured rates to effective queue rates, we can put those values into our latency prediction equation to validate that our predictions for packet latency through a software switch are aligned with observed values. In the figure on this slide, the x-axis is the configured queue rate, and the y-axis is the average latency of each packet through that queue. The blue markers represent our predicted latencies that are calculated from observed throughputs and effective queue rates, while the red markers are the actual observed latencies of packets in a flow. As we can see, our predicted and observed values for latency are very closely aligned. This demonstrates that our methodology for latency prediction is valid for a real-world bandwidth sliced system. Although our methodology for latency prediction is valid in real-world systems, it has some limitations in that it is only applicable if the queuing system can be represented as an MM1 queue. As we just demonstrated, OVSKP, which uses HTB as its packet scheduler, falls under this category. However, OVSDPDK, which uses 2-rate 3-color marker as its packet scheduler, does not. Although both of these packet schedulers utilize the token bucket filter algorithm, the tokens are used differently in each. In HTB, if a packet arrives at the head of the queue and there is no token available, the packet will simply wait at the head of the queue until a token becomes available. However, for a 2-rate 3-color marker, if a packet arrives at the head of the queue and there is no token available, the packet is immediately dropped. These differences in behavior can be clearly seen in a direct comparison of OVSKP and OVSDPDK packet latencies. For OVSKP, while there is a distinct correlation between allocated queue rate and observed packet latencies, that correlation is non-existent in OVSDPDK's observed packet latencies. This is because the rate of the queuing system in OVSDPDKs is independent of the allocated queue rate. The allocated queue rate's purpose is just to specify the rate at which packets need to be dropped or not. Since the OVSDPDK queue does not actually operate at the allocated rate, the time spent by each packet in the queue cannot be predicted using this rate. On the surface, OVSKP and OVSDPDK's rate control mechanisms accomplish the same goal: limit the rate of traffic that is sent to the egress NIC. However, the differences in implementation also have significant implications for resource utilization efficiency. When OVSDPDK drops all of the packets that are in excess of the allocated queue rate, this has a detrimental effect on the retransmission rate and congestion window size of TCP flows. For example, for a 500 megabit per second queue, the retransmission rate is greater than 10%. With this retransmission rate, large application layer messages are very likely to experience retransmissions and slowdowns due to resource utilization inefficiencies. Flows that are rate limited with OVSDPDK also have small and unstable congestion window sizes. Each time a packet is dropped and retransmitted, the congestion window of that TCP connection is halved. These frequent congestion window size adjustments also result in spikes and dips in flow throughput, which further reduce the predictability of packet latencies. In conclusion, we demonstrated that packet latency through a bandwidth-sliced software switch can be predicted. To do so, the effective queue rate must be calculated by determining the switch's queue granularity, and the packet scheduler must follow MM1 queuing scheme. We also show that the differences in packet scheduling mechanisms come with unique trade-offs. With OVSKP and OVSDPDK, the trade-off was between predictability and low latency. We hope that you enjoyed this presentation and that you had a wonderful day. Thank you.